This one is the syllabus of real analysis for BSc third semester. So, before doing the next theorem, that is Archimedean property of real numbers, look at this course as per your syllabus. The next topic is, see, from unit 1 we have already covered bounded and unbounded sets, supremum and infimum, these properties. Now we will do first Archimedean property of real numbers and representation of real numbers. So let us look at Archimedean property of real numbers. So these are the 4 chapters which we need to cover. First one is fundamental properties of real numbers, second one elements of point set topology on R, and unit 3rd, 4th is related to sequence and series of real numbers. So the with this Archimedean property we will do from this book, R.G. Bartlett, the book by A Basic Course in Real Analysis by Ajit Kumar and S. Kumaresan. So before starting, let us recall what we mean by list upper bound property of real number. As per statement of list upper bound of real numbers, given any non-empty subset of R, which is bounded above in R, then there exists its list upper bound, that is supremum from R, and we can write it as alpha is equal to list upper bound of A. Alpha is equal to list upper bound of the set A, where A is non-empty and bounded. Second condition on A is bounded. So every non-empty and bounded subset of R, if it is bounded above, then we have existence of list upper bound, that is supremum of the set A, and if it is bounded below, then we have the infimum, greatest lower bound. So we have seen the examples based on this one. Set Q of rational numbers satisfy all the properties, however it does not enjoy the list upper bound property. So this one is a very good example in which see, here in list upper bound property, this one is list upper bound property for R, set of real numbers. So question is, can similar property hold for the set Q, set of rational numbers? So this is not true. So this one is a very good example that this set is a non-empty subset, bounded subset of Q, but we can see that its supremum and infimum, though it is bounded above in Q, but it does not have list upper bound in Q. Why? Because we can write this set as, let me call this set as, say, A is subset of Q, and A is defined as collection of all those x belonging to Q such that x square is less than 2. So if we simplify this, we will I can write it as minus root 2 to root 2 open interval intersection Q. Actually we are interested in all those x which lies in this interval, all those rational numbers. So we can write this set as this one. Now it's root 2 and every real number, clearly this set is non-empty. Why? Because there is at least one rational number, say 0 in this set. So this set is non-empty. Now this set is bounded, it has upper bound as well as lower bound. Now just look at the upper bound. Every real number is its upper bound. So I can say that root 2 is also its upper bound in R, but our space is Q here. So collection of all those upper bounds, if I am talking about collection of all those upper bounds, collection of all upper bounds of this set, so I can write it as that root 2 to infinity. The root 2 is not rational, so I can write it in this way. So root 2, every real rational number greater than equal to root 2 is its upper bound. So what will be the list upper bound of this set? That will be root 2, and root 2 is not in Q. So in this way we can discard that this set is non-empty, bounded above, but it does not have a least upper bound in Q. We are getting least upper bound in R. Root 2 is a least upper bound in R, but not in Q. So completeness. So Q is in this way we can say that Q is not complete. So next theorem is Archimedean property of real numbers. Archimedean property of real numbers. Its statement. There are two principles. I am doing it from the book of S. Kumaresan and Ajit Kumar and S. Kumaresan. This I am referring from this one. So as per this, the first statement of Archimedean property of real numbers is that n is not bounded above in R. That is, given any x belonging to R, there exists n belonging to n such that here there is typing mistake. It has to be n greater than x. See, if this set is not bounded above, then whatever bound I will give, say this x is its upper bound. So if it is not bounded above, then I need to produce at least one natural number from this set n which exceed this x. So we need to do here this typographical correction. And second property is, given any given xy belonging to R with x greater than 0, then there exists n belonging to n such that n times x will exceed y. So we can just let us analyze the property number 2 before coming to the proof of both of them. Yes. So we need to, if we look at the property here, given xy belonging to R with x greater than 0, then there exists at least one natural number such that n times x will exceed y. Now there is no restriction on y. Y can be 0, y can be negative real number, y can be positive real number, but there is a restriction on x. So suppose this one is origin here, and y can be 0, or y can be negative, or y can be positive. So if y is negative, then I can take n as 1, and since x is strictly greater than 0, so n equal to 1 will work, nx will be always greater than y. For example, if I choose y equal to -5, then obviously any real number greater than 0, since x is already greater than 0, so we will get the natural number 1, which will serve our purpose. There exists at least 1. Now next one, if y is equal to 0, then again n equal to 1 will work, nx will be right to y. In case y is right to x, or y is in between x, then again n equal to 1 will work. But if y is right to this nx, y is right to this x, suppose this one is the x here, then 2x, since x is greater than equal to 0, then we have 2x here, 3x here, and so on. It keeps on increasing, and there will be a moment when nx will exceed y. So again nx will be greater than y, but we need to do it in the mathematical way. So let us start from the property number 1. We want to show that n is not bounded above. So on contrary, we will assume that n is not bounded above. So on contrary, we will do this by the method of contradiction. Assume that n is bounded above in R. So since n set of natural number is subset of R, and it is non-empty, so from the completeness property of R, every non-empty bounded subset, of R, if it is bounded above, then it will have least upper bound. So since we are assuming that this set is bounded above, in place of n greater than x, suppose n is every n belonging to n is less than equal to x. Then since this set is bounded above, so from the least upper bound property, it is also non-empty. So every non-empty bounded above subset will have least upper bound. So there is the existence of least upper bound for the set of natural number. Now suppose that alpha is that least upper bound. On contrary, suppose n is bounded above. suppose n is bounded above, then from least upper bound property, suppose alpha is the least upper bound from completeness property of R, alpha is the least upper bound of say the set of natural number. That is, if for each k has to be less than equal to alpha, because least upper bound is also an upper bound. From all upper bounds, the least one is called the least upper bound or supremum. Since we wish to exploit the fact that alpha is the least upper bound of n, now alpha is also a real number, then obviously alpha minus 1, if we subtract 1 from alpha, clearly alpha minus 1 is less than alpha. Then because we have already assumed alpha minus 1, alpha is already least upper bound, so any real number less than alpha cannot be an upper bound of n. Hence, there exists at least one natural number. This implies alpha minus 1 is not an upper bound, because we already have assumed alpha is the least upper bound. So, alpha minus 1 is not an upper bound. Alpha minus 1 is not an upper bound means, how to discard this? Whenever a bound is given, whenever someone claims that this is the upper bound, and we need to show that this is not an upper bound, so I need to produce at least one element from the set. Set is here set of natural number. So, there exists at least one, say, let us take the same notation, capital N. This one is at least one natural number, at least one n. This n is referred for the set, n belonging to n, such that n will exceed alpha minus 1, because it is not an upper bound. So, from this I have n plus 1, bring 1 to minus 1 to left hand side, n plus 1 greater than alpha. Since n is a natural number, so n plus 1 is again a natural number, and n plus 1 is exceeding alpha, whereas we have assumed that alpha is a least upper bound, means alpha is also an upper bound, and we are getting the member from set of natural number, say n plus 1, which is exceeding alpha. So, this implies we have a contradiction. Thus, our assumption that n is bounded above is not true. Contrary to it, n is not bounded above in R. So, this is the idea of the proof, which is clearly explained here, that hence our assumption that n is bounded above is wrong. Now, let us do the second part of this property. Of this principle, we need to prove that given x y belonging to R, given any two real number from R with one of them greater than 0, then there exists at least one natural number n such that n times x will exceed y. Very important result. Again, we will do it by the method of contradiction. Let us suppose that this result is false, means there exists at least one x which is not following this condition. I mean, for that x we will get whatever n for every nx is less than equal to y. So, that is written here, that if there exists such x, because we are assuming it is opposite to this one, if false, then there exists x greater than 0, y belonging to R, such that for each n we have nx less than equal to y. We have nx less, since here I can talk for x, because x is non-zero, x is clearly greater than 0. So, from here we can write that n is less than equal to y by x. Now, y is a real number, x is a real number, y by x will be a real number, and this y by x is well defined because x is not equal to 0. In fact, x is greater than 0 for all n belonging to n. So, every natural number has upper bound as y by x. This means set of natural number is bounded above, which is going to contradict the first principle of the Archimedean property, that n is not bounded above in R. From this we are getting upper bound. So, again we have a contradiction. This means that there exists at least one natural number, whatever x greater than 0 is given to us, y can be 0, y can be negative, y can be positive. There always exists at least one natural number that nx will exceed y. So, this is the proof of these two Actually, in books you will find mainly property 2 as referred as this Archimedean property of real numbers, but this one is also, and we will use these two in various proofs. So, these two are very important results. Let me do one more example here, some of the example. I have explained the proof here, but again let us recall what we have studied earlier. Let us start from a finite set. Say A is equal to say 2, 3, 4. Then in this case, every real number, its upper bound, in fact 4 and greater than equal to 4, every real number is its upper bound. So, I can write set of all upper bounds of A as collection of all those x such that x is greater than equal to 4, A is subset of R. This means or I can write it as 4 to infinity. Now, the least upper bound among all these upper bounds is 4. So, least upper bound of this set A is 4, and this is also referred as supremum by various authors, supremum of the set A. So, this one is the example. Similarly, one can take another example, say, and this set is also bounded above. If there exists at least one upper bound, say 4, or in fact here every real number greater than equal to 4 is its upper bound, but to show that a set is bounded above, we need to just produce at least one upper bound. Similarly, one can construct, one can take a countable infinite or uncountable set. For example, if I choose B is equal to open interval 0 to say 2, then in this case set of all upper bounds, what will be set of all upper bounds? This set is bounded above, and every real number greater than equal to 2 is its upper bound. So, I can collect all those upper bounds, and those upper bounds will be all real number greater than equal to 2 or 2 to infinity. Now, from all these upper bound, the least one is 2. So, I can write that supremum of set B or least upper bound, in short LUB, of this set LUB of the set B is equal to 2. So, this is the idea. Here you can see that least upper bound is not member of set, but if I choose it as say C is equal to closed interval 0 to 2, then in this case again set of all upper bounds will be again 2 to infinity, and from this we will find that the least upper bound is 2. So, here supremum is member of this set. So, supremum may or may not be member of the set. Whenever supremum is member of the set, then we can also call it as maximum of the set. So, maximum of a set whenever exists, that will be member of the set, but in case of supremum, that is the least upper bound, it may or may not be member of the set. For example, in this one 4 is the member of the set, this one is an infinite set, uncountable set, again this one is an infinite set. In this case supremum is not member of the set, 2 is not member of the set, but in this case the next example, set C equal to 0 closed interval 0 to 2, supremum is the member of the set. Similarly, one can construct several examples. I am giving these 3-4 examples to understand the theory, that 1 2 say similarly one can take this set 1 by n belonging to n. This set is, I can write it as 1 1 by 2 1 by 3 and so on. So, we can see that this set is bounded below as well as above. Every real number greater than equal to 1 is its upper bound. So, the least among them will be 1. So, its supremum will be 1, and infimum 0 and any real number less than 0 is its lower bound. So, among those lower bound, the greatest one is 0. So, its infimum will be 0. So, this set, since this set is bounded above and non-empty subset of R, so from the completeness property of R, it has supremum as well as infimum, supremum as well as infimum. So, this is the idea how to compute supremum or infimum of a set. And again here one can look at the set, say okay, we will do the remaining result in the next part.